All right, thank you for this chance to be here. And I was asked to talk about monitoring, and by necessity, I'm going to be talking primarily about my work with the red bay ambrosia beetle attractants. I want to point out right up front that I didn't do all this work by myself, that a lot of other colleagues working with me over the years, and I greatly appreciate all of their help and efforts in doing this work. So just some real quick background. The red bay ambrosia beetle was found was actually caught for the first time in Port Wentworth near Savannah, Georgia in 2002 in the detection traps at the port. And it was really not until 2004 that we realized that it was transmitting the laurel wilt fungus and that it was killing red bay trees. It is from Asia, and it's killing both red bay and sassafras trees in our forests now. And now it's very widely distributed. You can see started there in the Savannah area, and by 2004 it was pretty widely distributed. I mean, there were a lot of dead and dying trees at that point. So that trap catch in 2002 turns out was just an incidental thing, that the traps weren't really attractive. It just bumped into them and fell in. And then so what we were facing was the fact that when this beetle gets into an area, the trees die out very quickly. So here's this is all trees, that dark line in the middle. And so when this experiment was set up, there were about 10% of the trees were dead. A year and a half later, 90% of the trees were dead. All of the large trees went out first. So all the largest red bay died first, and then you still have a small percentage of these 1 and 2 inch diameter trees, and then over about a 5-year period, those will all die too. So that within an 8-year period, you have no more red bay trees over 1 inch in diameter, except for a few escapes or resistant ones possibly. So, so with that background, we were sort of faced with trying to come up with something, and we wanted to come up with it pretty quickly. And so our first thing we did was we went and said, well, let's go look and see what attracts ambrosia beetles. And we went to Faro Base and looked, and I did this recently, and I took a real quick look, and there were 21 beetles listed, and 18 of them were attracted to ethanol, and we thought, boy, this is going to be easy. So we'll just put up ethanol traps. Turns out that we did that, and ethanol wasn't attractive to the beetles. So we were sort of faced with starting from scratch. And we did some early observations, and we knew that wounded trees were attractive to the beetles. So we started to look at a couple of things. So wounding, healthy and diseased trees. We also wanted to see if the beetle was producing anything. So we put up infested and uninfested trees, and then we looked at some other species. I'm really only going to talk about these first two. So initially we took trees and we put wounds on them, and they were either healthy or diseased trees at the beginning of the experiment, and then we also had unwounded red bay trees, and we had non-host oak trees. And what we found was that indeed wounding did increase attraction, although not significantly over a healthy tree. It still was quite a bit higher, certainly more than we caught on the non-host trees. We did initially, the non-diseased trees, the healthy trees were healthy at the beginning, but when you wound them, then you get beetles coming in. So it really wasn't definitive whether or not the disease was producing anything in this experiment, but we did show that wounding was increasing attraction. So we went and took healthy red bay trees, and we cut up sections and put them in screen cages to prevent beetles from being able to attack them. And then we put in heavily infested trees, and we put those in screen cages and hung those up with traps on them to see whether or not the beetles would be more attracted to trees with a lot of beetles in them. And so this just shows you the amount of frass that's coming out of those things and accumulating in the bottoms of those bags. And what we found was that it didn't matter whether or not there were beetles in the logs or not. They were equally attractive. And I would point out that these attack trees also had the fungus too. So beetle plus fungus didn't really increase attraction over a healthy, uninfested log. Now Yuri's done some more work recently that indicates that there is an attractant from the fungus, and so there may be some more subtle things going on here that we didn't pick up in this experiment. But okay, so what we basically found is the beetles weren't producing an attractant, or we didn't think they were, and then that the bolts, whether they were healthy or infested, were equally attractive. And the other thing that was interesting was that we ran that experiment for 70 days, and we caught just as many beetles at the end of 70 days as we did at the beginning. So logs remain attractive for a very long period of time. So that led us into looking for attractants from the red bay. And so we teamed up with Brian Sullivan with Forest Service over in Pineville, Louisiana, and we did aerations of red bay wood and bark. And we pretty much ignored these monoterpenes at the beginning because we had already hung up pine logs and found that they weren't attractive at all, and they produce a lot of monoterpenes. So we felt like they weren't very important. So we focused on these, primarily sesquiterpenes here in the middle. Three of those, cubabene, copene, and calamine, we couldn't get in large quantities for testing, at least in pure form. So we did some searching in the literature, and that's when we came up with Manuka oil. And so we saw that Manuka oil produced those compounds, and so we decided to test that. And then we got wind of some of Damon Crook's work and talked to him, and then he pointed out later on, about the Phoebe oil. But we started out with Manuka oil, and in our first trial, we tried it, and it wasn't super attractive, but we did see a little bit of a bump there in catch, so we said, well, let's try it again at a little higher release rate. And when we did that, the second trial, we had about a 30% increase in or not a 30%, but about a 30-fold increase in the number of beetles that we caught over the methanol blanks. So we were pretty excited when we saw that. And so we started looking at focusing on this Manuka oil as well as testing Phoebe oil. And in those first two trials, the first one we ran it with red bay wood as for comparison, because that was our most attractive source at that time. Manuka oil and Phoebe oil were, although Phoebe oil caught a lot more beetles, they were not statistically significant. And neither one was more attractive than red bay, but they caught as much as red bay would. We decided to pursue just Manuka oil because of the fact that we were hearing things about the supply, that Phoebe oil was not going to be easily available for a long period of time. There was also some concern because of the trees considered by some in Brazil to be threatened in its natural habitat. So we decided to focus our efforts on Manuka oil because of that. In looking then at the attractive compounds, trying to figure out what was really going on, when we looked at our trials and at our aerations, you can see these three compounds that I talked about in all of them. But when you do look at Phoebe oil, you notice that cubabene and calamine are in fairly small quantities relative to copene. And so we sort of speculated that copene is the primary attractant, but really at this point, nobody's really been able to prove that. Okay, so then we started looking at release rates, and we did a couple different experiments. This one was from 5 to 50 milligrams per day release. And you can see that we got about the same numbers of beetles regardless of the release rate at the release. So we jacked up the rates quite a bit, and we went up to 200 milligrams per day, and we did 2 trials like that. And again, it didn't matter whether you were releasing 5 milligrams per day or 200 milligrams per day, you caught about the same numbers of beetles, which is kind of interesting. But we didn't want to just stop there, so we did it again. And we spread the releasers out across the funnel trap to see if maybe having them spread out more would make a difference. And it didn't really matter. As long as you had one releaser in the middle of the trap, you caught just as many beetles as we did with 3 releasers on the trap. We looked at trap height. We wanted to make sure we were trapping in the right location, and we did this experiment twice to just show you this one, where we caught 85% of the beetles we caught down at the about 1 to 1.5 meters above the ground. So. We also looked at trap color. We wanted a purple trap just like the EAB guys had. So we tried different trap colors. We did 2 different experiments. This is just one of them, but basically from the 2 experiments, we decided that color really wasn't making much of a difference in terms of trap catch. So, and we were doing a lot of work with white sticky traps, and they work, but they don't catch a lot of beetles relative to these flight intercept traps that we were using later on. So we did just looked at trap type real quick, and although we didn't see significant difference in the numbers of beetles caught with these different types of traps, these Lindgren funnel traps worked as well or better than the other ones in terms of numbers of beetles caught. So we concluded that, you know, because it's readily available, it's easy to work with. We decided to go ahead and to focus our attention on these funnel traps. So we had done a study where we used the wounded trees throughout the year as an attractant source, and we just trapped beetles coming or flying around those trees. And we found that there was a flight activity peaked right around late August, early September doing that. When we did that with traps baited with Manuka, we essentially found exactly the same thing, that the peak occurred right around September. So we felt like the Manuka oil traps were reflecting what was actually going on out there in the woods pretty well. One of the things we were interested in is whether or not these things would work at low densities as well as high densities. So we had this experiment where we were monitoring populations of the beetles. We're actually looking at attack densities of the beetles at these different locations where they had either killed all the trees initially, so there were hardly any red bay trees, and then other places where there were still red bay trees, but most of them were dead, and then these places where they had just started to come in 2007. And so we did this study we put funnel traps out at these locations at the same time that we had these bolts hanging up that we used for monitoring the attack densities, and then we put sticky traps on those to see, you know, give us an idea of what was coming to the bolt and then what we were catching in the traps. And what we found was that the 2 types of traps performed about equally well. So you put a sticky trap right on the bolt and you get about the same correlation as you do with a funnel trap. So we felt like they were performing pretty well at all population densities. We were interested in finding out just how far these things would fly away from a source of red bay trees. And so we had this study area where we had this sort of drainage that was a lot of red bay trees. In fact, I'd say probably 50 to 60% of the trees in there are red bay. And then we had this area where they had cleared the forest, and there were just mostly turkey oaks out in here. And we set up a grid of traps at 100-foot spacings from the edge of the forest all the way out to 1,000 feet to get some idea. And then what we did was we put traps at 1,000 feet, at 500, and then at 100. We left the 100-foot traps there, and then each week we would progressively move in the 1,000 and the 500, so they got progressively closer to the 100-foot traps. And so what we found, and first week we were all kind of excited. So, wow, look at that! At 1,000 feet, they kind of drop off. So that's kind of an edge there or something, because we got fewer beetles there. But then in the next week, with 900 beetles, we caught just as many as we did at 100 feet from the edge of the forest. And then when we went to 800 feet, we caught more than we did at the 100 foot. So And then at 700, or yeah, at 700 feet, there was no difference again. So we just pretty much concluded that that was just an artifact. It wasn't anything important. So then we put all of the traps out and trapped. And what we found was that we were catching equal numbers of beetles throughout that grid of traps all the way out to 1,000 feet from the source of beetles. So it tells you that that these beetles are dispersing throughout these forests. What was kind of disturbing, or they're dispersing a long way from these forests. They're not staying necessarily near where there's lots of hosts. They're leaving for some reason. But what was kind of disturbing to me was that there are 45 traps between the edge of the forest and that 1,000-foot trap line, and we didn't slow the beetles down at all. I mean, it doesn't look to me like we had any impact on the catch out there. So there's a lot of beetles flying around out there, and it would probably take a lot of traps to reduce the numbers getting through the forest. One thing we were interested in was whether or not alcohol would synergize Manuka oil or inhibit in any way. So we did a study to look at that, and as I mentioned before, alcohol was not attractive to the beetle at all. But if you add alcohol to Manuka, it doesn't inhibit attraction. It doesn't increase it either, but at least it doesn't have any negative effect. And then another thing we were interested in was whether or not Manuka oil could be used in combination with alcohol and still catch the same numbers of species. So we did a study where we had 6 different locations around the state of Georgia, and we trapped the beetles. And so this is the species richness in our traps. And with Manuka oil, we caught an average of 2 species per trapping location. One of those is the red bay ambrosia beetle, so we didn't catch a lot of other beetles with that. With alcohol, we caught about 6, and with the 2 together, we catch about 7, one of which is the red bay ambrosia beetle. So bottom line is you can combine Manuka with ethyl alcohol and not really inhibit other beetles, it looks like, but it doesn't really enhance attraction to other ambrosia beetles either. So kind of to summarize then, what we found that the essential oils extracted from Manuka shrubs or from Brazilian walnut trees are attractive to the red bay, are as attractive as red bay wood in this case. We feel like copain is probably the likely attractant, but as I said, nobody's really been able to prove that just yet. The 8-unit funnel traps work baited with a single Manuka lure work well and work as well as red bay would. And traps 1 meter above the ground are effective, and that Manuka oil can be used in combination with ethanol and without reducing the number of species. Now when we started this, or at least when I started this, my main goal was to find something that we could use in conjunction with insecticides to do an attract and kill kind of approach. And we're still interested in that. We're still waiting to find something that actually kills the beetles. But we feel like from a forestry perspective, that's a more practical way to go would be to be able to spray non-host trees with an insecticide, put a bait on there, and draw beetles in and have them die at the non-host before they can infect a healthy tree. As far as monitoring goes, though, in reality, the states are doing the monitoring, and what they're doing is looking for dead and dying red bay trees because, well, they look like that. They stand out like a sore thumb, and they keep their leaves for over a year. So it's real easy to drive around the roads and spot those dead trees. But they do have this option, and I think now that the beetle's getting outside of the range of red bay and going into sassafras, which doesn't keep its leaves and is much harder to see, the traps may actually become more useful for that. So with that, try to answer any questions if you have them.
I'm wondering, I've heard from Dave Wakershuk from Semichem that the methanol might actually be slightly repellent to some beetles. I don't know if you've, and I noticed that you have methanol as a control. I wonder if you guys tried the.
We did. In our initial trial with alcohols, we tried methanol and ethanol, and we didn't see any repellency, but certainly didn't see any attraction either.
Yeah, oh, that's good. And the other thing is that I know you've shown that the color doesn't really matter, but I wonder, I've been often using just transparent plastic bottles as the dirt cheap alternative, and I wonder if the color versus transparency matters. Do you have any idea?
Not that I'm aware of. Now a lot of our early trials with red bay bolts and things like that, we used transparent traps. We used those plexiglass traps that we just hung on the sides, and I mean, they certainly worked well, but I can't say that we ever tried, putting colored bowls or any kind of color on that either. So hard to say.
Do you actually have evidence that putting those traps out reduced the incidence of the disease in one of your research plots?
No, none at all. We haven't tried that. We actually just set up a trap out study, but what we're doing now is, the beetle, once the beetle gets into an area, it kills everything. I mean, there's nothing but very small red bay trees left. So now when they do that, the beetle populations drop way off, and down to where we're getting less than 1 beetle per 100 square centimeters in those logs after we hang them out for a month. So now we're thinking, well, maybe we can use this sort of as a mop-up on these barrier islands and actually kind of see if we can trap out the population and actually get it down to zero, and maybe let these red bay trees kind of recover and start to grow again. So we do have a study. We just set that up, and I'm supposed to be out there hanging up bolts, but other people went and did it instead so I could come here. So.
One more question in the back.
In using lingering funnel traps or the purple people eaters, either one, hanging them in an urban situation is problematic. Do you have a recommendation for a trap in an urban situation?
Well, almost all of our trapping is done, or a lot of it anyway, has been done in state parks where there are quite a few people walking around. So we haven't had any problems with people messing with our traps, if that's what you're talking about. Yeah, I would think that might be an issue in some urban areas, but and they're expensive traps. So maybe in your case you want to go with sticky traps. I don't know.
Ruben, you had a question?
Yeah, I never hear any comments about wind patterns, like it doesn't function. Here we get severe winds sometimes, either Santa Ana coming or normal. Is there such a way to follow, or do you follow how the wind moves, and if you have more movement in that direction independent of the flight?
No, we haven't done that at all. I mean, the beetles have managed to get to all these barrier islands, even though some of them are pretty far off the coast. So we think that, that probably some of it is wind movement, that they're being picked up by storms that are coming through and going out off the coast, and that's one of the ways they're moved around. But we really have no proof of that. So.
One comment to that, if I may. There's some little data on other bark beetles that show that even though they do get picked up by random big winds and storms and such, the beetles themselves don't like to fly in the wind. So if the wind is over a certain speed, they drop and don't fly anymore. So I would not expect much of an effect on the direction of the wind.
Okay, we better move on here. We're way over time and it's just getting late. So the